So let me share the screen. And I'll also visit some of the things that we did on Friday. Friday's class was very elementary. Today will be slightly, will be more fast, maybe we should say. Yeah. Okay. Yeah. Let us just start with a question. Okay. So this is a problem. I should say a one-dimensional walk. A one-dimensional walk. So in the past, I mean, maybe 4 or 5 classes in counting, we have been looking at number of paths from one place to the other with different kinds of rules, walking in this way, walking north and east, and then we change the moves and so on. We have two-dimensional walks. Today, let us do a problem on one-dimensional walk. Okay, so but it's not easier, you see. And this is the fundamental problem in theory of probability, Markov chains, and so on later on. But let's see. So here we are starting from the origin. Okay, and this is just a line, and these are some points. Dot n, and maybe it goes on, doesn't matter. And similarly, it could also go. Well, let me just draw it. You may use it in the, I don't know. So this is the thing. Now, what is the situation? The situation is that we want to start at the origin. So all these are going to be counting problems. Okay, we are going to start at 0. Okay, each move is either one step to the right or one step to left. Okay, each move is one step. 1 minute. Let's just enter someone. Yeah, each move is either one step to the right or one step to the left. Let me write it mathematically. Each move is either k going to k plus 1 or k going to k minus. And this is the, I mean, we are just doing it as a puzzle, just as a problem, but this is a fundament, mathematically very important. I mean, theoretically, I should say, not mathematically. So each move is either this or this. Okay. Now the question is, how many ways, okay, to start at 0? Okay, how many ways are there to start at 0 and end at 0 after, let's say, 10 steps? Okay, so we have 10 steps. Okay, we have 10 steps, and we are going to start at 0 and we want to come back to 0. How many ways are there? Now, how many ways, I mean, how many different journeys are there? Let me just give an example. Okay, so this means how many different journeys. Now, we have seen this theme earlier, but so I mean, what I mean is that the exact sequence of moves matter. Okay, how many different sequence of moves? So let me give an example. For example, you can go from 0 to 1, then you can go from 0, then you can go from 1 to 2, then third move you come back, fourth move you come back, fifth move, sixth move, seventh, eighth, ninth, and then 10th. So this is a journey. This is one journey, right? This is 0, 1, 2, then you came back, then you came back to 0, then you went to -1, then you went to -2, then you went to -1 again, and so on, right? You can understand. So on. So this exact sequence matters. Okay, you made 10 moves, you have 11 points, but you made 10 moves. This in total, how many ways are there? Is the question clear? Just first see that, and then in total how many?
So you're mentioning that in this problem, can you just explain it a bit again?
Yes, sure. So basically, I'm saying that you want to start at the origin and you will make a sequence of moves and come back to the origin. right?
Okay, yes.
But you are only allowed to make 10 moves, and you have to come back to the origin. And then I'm asking, how many different sequence of moves can you make? Like, I have given to you one sequence of moves where you start at 0, you go to 1, you go to 2, then you come back to 1, come back to 0, you go to -1, -2, and you can see that. Okay. But remember, each move only you can take one step to the right or one step to the left, nothing more than that. Okay. Like, we did one problem where we could jump a step, but that was different. Now, this is not the exact question which I wanted to discuss. This is actually extremely simple, I think. But just try it. Don't go by what I'm saying. Extremely simple. So the exact sequence of moves matters. So just try it in your own ways. You can take small cases and try. If that's your thing, you can just think in whatever way. You can write out a sequence and count number of such sequences with some conditions, or you can try by recurrences if you have done that. Anyways, fine, right? But if you do for small cases, you will get a clear yes. Yes, please. Why? Okay, so let me write that. I think that is important, right? So that's the key observation. Yeah, 5 R's and 5 L's. Okay. Okay. So why is it 5 choose 2 times 5 choose 2? So basically it's a 10, right? You have 10 blanks. So 10 steps means, for us it means, I should not write equal to, but 10 blanks. Okay, now think if this is correct what you have said or not. 10 spaces. So is it clear to everyone that we have 10 spaces, 10 moves, 10 spaces, and basically we have to make 5 rights and 5 lefts. And if you make 5 rights and 5 lefts, you will come to the or come back to the origin. Right? So let me write that also. Coming back to origin or 0 is the same. So it's the exact same thing as 5 R's and 5 L's. Now you guys think. This is not correct, but the idea is correct. There is a technical mistake in that, but the idea is correct. Okay, think. No, no, it is just 5 choose 2, right? And am I saying something? No. It is not even 5 choose 2. Wait, why 5 choose 2? That's a technical mistake. Think again. Let's all of us think. There are 10 spaces. Yes, right. So there are two choices here, either right or left. And for the second space also, there is a two choices, right or left. And here also right or left, and so on. No, You're making a counting mistake. You have got the right idea, but you're making a counting mistake. No, so it is just so there are 10 things, right? And you have to, okay, I will not say. Let's take some more time. Let's think. Meanwhile, I'll just make one more thing, a conceptual point here, that, let me say this, okay? A sequence of rights and lefts, okay? Every sequence of rights and lefts gives a unique journey, right? That you have to mention, right? So sequence of 5 R's, 5 L's. I should just write a journey, but I'll write a unique journey. Right? It will decide exactly where all you will go and what all you will do throughout. Now, all this you have to mention, and if needed, you have to explain. After this, there is just a counting thing that you have to do. You don't have to do it like this, but this is a roughly thing. But now it is a very simple counting problem where you have 10 spaces and 5 R's and 5 L's. Let me just write 5 R's in front and then 5 L's. Now you want to throw these on this sequence, in these spaces. You want to fill this 10 spaces with these. We have done this problem several times in different guises. I mean, this particular counting. Yeah. Yes, exactly. That's absolutely correct. Can you give some explanation to us? In 6 places there, right? And here it's 10 places, right? So that's perfectly correct explanation. Would anyone else want to give a different explanation of why the answer is 10, choose 5 now that you know the answer?
Like, can we consider all the elements as distinct elements, and if we are dividing them in like 10 sequences, like 10 places, then that would be 10 factorial.
Hmm.
Among those, like, elements, there are 5 distinct ones, so it would divide it by 5 factorial, and then again, that's more like a mechanical
Yeah, and that's right, and that's not completely rigorous, right? But that's like a sanity check. Let's say you can check it with that. That's perfectly correct, right? And but what you're saying can be made rigorous, but that gets a little complicated, okay? But to say it more simply, and this is again a theme that I had done earlier, is view it like a choosing. Choose 5 places for the R's. Right? You have 10 distinct, and the places are distinct, right? It matters, obviously, which place, what is there, right? So I just need to tell you people one thing there. Just choose 5 places for the R's from the 10 places, right? And that will just do everything, right? From 10 places, choose 5 places. And that's just that all of us know that's just 10 choose 5. Okay. Now this is a very quick way to answer this. And obviously now you can remember this, and this is a formula you can use. This has disadvantages. It doesn't generalize. The idea that Ritam was saying about first showing all distinct and then dividing, that's actually a more powerful idea of symmetries and so on. But for now, we can stick with this. Okay, that will require you to give more explanations if it's not an MCQ. Okay. So is it okay with everyone now that the answer is just 10 choose 5? Okay, very good. Okay, it's okay to everyone, right? 1 minute. Kathy, it's okay for you also, because uh, okay, thank you. Okay, good. All right. So then this was not the problem I was going to discuss. It's simple. We have actually done this kind of problem several times, but it's a good brush up, long gap. Now we want to say after, I mean, I could just added things there, but now here is what you can wonder. After 10 steps and exactly 10 steps, never before. So you are not allowed to come back to the origin at the 8th step or 9th step. 9th step, you know, you cannot come back. It has to be an even number of steps, but you cannot come back to the origin before 10 steps. Now, this problem is very fundamentally important. This was one of the, I think, Madhavan mathematics competition. This was there, but it's just there in all the places. Yeah, I mean, yeah. So this is a counting problem, which is we have to think about. Never before. No, you can go to the left. Actually, you can go means I have not drawn it. Yeah, let me, I could have said that first move has to be to the right, but you can think that is a symmetric thing, right? Yeah, right. Yeah. So basically, so the observation from what Shanna said is that just focus on positive part. Because see, if you can answer there, then you can just multiply by 2, right? For the negative part. Just focus on the, I just say this and now you can think. Now again, this is a problem which is slightly complicated. We will not solve it today, but we will see connections. Okay, so yes.
It's kind of like the problem where northeast and southeast were allowed and we cannot touch the exit.
We can touch but not cross. We, it is, you are right.
Like if we start with left, we cannot have.
Yes. So as you were saying, it's very similar. In fact, what you said is exactly the thing, but let's not refer to it now. Yes. So how do you for write these in the conditions? Basically, it's again, we need 5 R's and 5 L's. So we need 5 R's and 5 L's. But then what is the extra condition? Is that at any stage, at any scan you do from left to right, at any stage, number of, I'll just write full number of R's is, say in this case, it is strictly more than number of L's. Does everybody agree with this? Right? Not, I mean, at any stage, meaning that except for the last, obviously in the end, it will be equal and you'll be back to the origin, but not before that. Is everybody fine? Yeah.
We start with L.
No, we can't start with L. Okay. Yeah. So starting with L, we are not focusing on that case because that case will be symmetric. Absolutely, just multiply by 2, right? If you start with L, then you have to remain in the negative world throughout, in the negative part throughout, right? And that case will be completely symmetric to this. I mean, you understand, right? Just think about that. So that is, you can multiply by 2. So we are not focusing on that part. We have divided the problem into 2 parts and we're focusing on this part. Okay, is everybody clear with this? Does everybody understand this? That at any stage you cannot have, means that in every stage, I should say, you should have strictly more R's than else. This is the condition you need, and if you meet this condition, then you're good. Okay, this is just a rephrasing, right? It's nothing new. So example, you can just take a very simple example. Just take 5 hours and then take 5 hours. But you can take many other examples, right? Okay. Not coming back before means that at every stage you should have more hours. Otherwise, you'll be back. If your number of hours become equal to number of hours, you'll be back to the origin, right? So we don't want that. Except at the end. Now, how do we solve this problem? Or can we give an answer to this, or at least to smaller cases, something like that? Okay, suppose I made n equal to 2 here. Then what would be the answer? Go on there, that's simple. Just 2, right? If we take the negative also. Right. Right, exactly. So if you take n equal to 2, then there will be 2 ways, but let me just write 1. Okay, because let's stick with this. Okay. So maybe, since you have already clear with that, but if you are slightly incompetent, think about it, write it. Okay, write it. When you write it, you will understand if you have really understood. Yeah. So like, don't just say it symmetrically. No, for every move, every legal moves you make on this side, you can produce a legal move on that side, and so on. Write it. Even if you think it's simple, write it. Try to explain it. Okay. Okay. Now, what about n equal to 3? Come on. 0, n equal to 3 is not possible. Yes, yes. Someone. No, but yeah. You will need an even number, right? Exactly. Odd is not possible. So odd is not possible. Again, just check it, explain it in your way, but odd is not possible because total number should be even. Total number should be even, right? Because again, you need an equal number of evens, equal number of rights and lefts. You need that is non-negotiable, right? That is certainly a necessary condition. First condition. It's not enough in this problem, but that's definitely a condition. So we forget about the even. Okay, what about 4? Let's quickly do this. It's not difficult. Again, it will be 1, right? There is no other way. You have to just go here to go one step. Now you better start coming back. There is no other way. It's just 1. What about 6? Now this is, I'm just asking these questions, but you can answer this by some, yeah, you can answer this not by brute force. You can think and find patterns also and answer. Okay, say. There are 2 ways. This is not 1. Yeah. There are 2, right? What are the 2 ways? So this is definitely, 1 is like this. Yeah. What will be the other way? Or is there another way? Mm. No, I think, yeah, this is again, yeah, because if you come like this, yeah, this will also be have to be 1, right? Yeah. This will, because you can't. Just check me if I'm wrong. Okay, this I think is also 1. Oh, no. That is, it's not so simple. Uh, This is 1 because from here, if you come back, then 3. Wait. 4. Wait, what is happening? 1 minute. 3. Then you can make another one 4. Then you can make a. No. So there is another one, right? 5 and a 6. Sorry, someone said 2, right? That was correct. There is. So I'll. Yeah. No, just. So there is another way. You can go like this, like this, again like this. So this is 4, 5, 6, right? Yeah. Yeah, that is okay. Let's do for 8. Now they might look boring questions, but you try to do them, and maybe you can find better ways to do. Eventually, that's what we want. We want a formula in the end. Especially those who have seen the other versions of this lattice counting, you can connect with that and try to say, but you have to say it in this context only, because in the exam or something you have to write it.
We went from 1 to 2 and the second year.
Yes. Yes. 4. I think that is correct. Or is it 5? Maybe one more. 4. Let me check. I think you have missed one move, one particular sequence. So again, repeating, coming back and forth is allowed because it creates different journeys. So let's try to count this, okay? And let's do it in a slightly, maybe smarter way. Okay, let's do it in a slightly smarter way so that we can do it quickly. See, first of all, notice that in this question, okay, let's write it like this. N equal to 8. Let me put 8 blank spaces. Okay. Now the first move has to be a right. Right? The second move, yeah, has to also be right. Perfect. What about the last move? L. And what about the second last move? Yes, right? That has to also be L. So we're trying to see this via sequences, and maybe it will help. So, well, this, yes. Yes, exactly. So then this, now you can remove this, and let me say it in this language only. Then the problem basically is you have to start from 1, come back to 1, but never cross 1. Yeah, but never hit 0. Let's write that. Though it is maybe simple to some of us, but still let me just write that. If there are 8 steps, then basically this becomes 6 steps. The problem becomes 6 steps. Start at 1. Now, those who have seen the lattice problems, you can connect with that also, but I'm trying to just say it in this context. Okay, start at 1, end at 1, never hit 0. Does everybody agree? Yeah. So now we can come back to 1, or you can come back to the x-axis. For those who have seen that. Right? You can come back to 1, but you're never allowed to cross it. So this is slightly, maybe you could say this is it's more easier to think about this problem maybe. Okay, so now you see this problem is like R and L, right? Now in between, so you can start at 1, let me just repeat it. Start at 1, 6 steps, start at 1 and come back to 1 in 6 steps, but never go to the left. So what does it translate to? It means that the number of R's will never be less than the number of L's. It can become equal. Okay. Right. So now let's just try to count. Now you guys try to count this. Someone already said 4, I think. So maybe it should be, I think it's 5. Can anybody find 5 moves? Or so the problem for 8 steps, you see here, it reduces to 6 steps. Okay. Okay, so surely you can find the 5 moves. Let me not do it by the brute force method. That is, you guys can obviously do it. But let's just analyze this. Now you see it. This can happen in several ways. One big chunk is never hit 1. Never hit 1. Never hit 1. This means never hit 1 before the 6th step. Let's just write before 6th step. What should be the answer to this? Obviously, you can count it, but see, this basically means that here it has to be R's and L's, 2 R's, 2 L's. Right? It will be 2 R's and 2 L's, and this will again have the same conditions. Right? Let me say that in a different way. If you look at this big chunk, this case, where you have to start at 1 and end at 1, but then if you look at this case where you never hit 1 before the 6th step, well, isn't it just the same problem as start at 0, come back to 0 in 6 steps, but never hit 0 before the 6th step? It's just the exact same problem, right? So this will be 2. This will be 2 for the reason that this is just the previous case. Does everybody understand this? Right? This thing of never hitting 1 before the 6th step, now you can just replace everything by 0, right? So this is just like the previous case. So this is just 2. So we already have 2 moves. Okay, now you see you can again break it down further. So that case is done. The other maybe the color. The other is when you, so R and L here never hit 1 in before, never hit 1 before the 6th step. So they never become equal before the 6th step. But then what are the other things? The other things is they become equal somewhere in between. If they become equal here, R and L become equal here at this step. So then again, this reduces to a smaller case. Right? If the third move is L, right? Then again, this is 2 R's and 2 L's. Right? I mean, you have to start with, yeah, this is again the same problem, right? We have to start with 2 R, you have to start with an R, L, and so on. This is again just like the previous thing. No, but that case is already done, right? No, now you can hit 1 before. Okay, right? So the way we broke it is you have to start, you have 6 steps, you have to start at 1, you have to end at 1, but never hit 0. Now, one big sub case is you never hit 1 before the 6th step. And that is 2 because that is just the previous case. But if you go like this and you go like this, then what is the problem like? Then it is like you have 4 steps and you have to do the same problem. Right? Because you have already wasted 2 steps. Sometimes you already spent 2 steps, right? And you're back at 1. The problem is the same again. You have to start at 1, you have to come back to 1, never hit 0. Right? So this will become the smaller problem. From this problem, you go to in this problem, right? Okay. So this will be again 2. So what is 2 here? When, if the second move is L, if the, maybe I should say third here. If the third step is L. Well, no, this is not actually the third step for us in this problem, right? Now we are 6 steps. So second, yeah, if second step is L, it's again 2. Because if the second step is L, then it's like again starting the problem. It's like doing the same problem, but for 4 steps. But that is just the problem for 6 steps when you have to come back to 0. Right? And what is the other case is when this is not L, when this is R. Right? But then you can just work it out with brute force, right? If this is R, then what are the possibilities? So yeah, this is the other case, right? When second step is R. See, if the second step is R, the third step cannot be R. Why? Because the third step is R, then this becomes the first case. Right? Because then it will be LL and this is like never hit 1 before. So it means that if the second step is R, then this one has to be L, and then this one has to be, no. Let's think. Yeah, so let's think. RRL. Now again, this cannot be R. Again, it will go back to the first case. So this has to be L, and then it has to be R. So this is just one. So we get the 5. Now, obviously, this is not a good way to do the problem, but you can kind of see that This kind of problem in general will be reducible to the smaller versions of the same problem, right? So you have to kind of do casework on the first time you hit one again, right? Never hit one again in the second move, hit one again in the fourth move, and so on. And based on that, you have to build a recurrence, but we'll come to that later. Okay, so the answer to this is 5. Okay, now you can check this again for homework. This will be 14, but please do this. Okay, do this, and maybe if you want, you can show it to me. Okay, I'm already telling you the answer. Okay, but that doesn't mean that you should take shortcuts and not write. Do this too. There is a real merit in doing this without knowing the formula. Okay, when I say do it, I don't mean that you have to do it by brute force. You have to consider all cases and so on. Okay, like you have to consider 12, choose 6 cases and then do. No, you can be smart. You can do casework like this, slice the problem in smart ways, and then do reduce to small case and so on. Okay, think about it. Okay, let me. Okay, so let's take a minute and see if there are any questions. No questions. Okay, so in summary, see, the main thing here is to reduce this problem, and this is, I think, important, to reduce this problem to allowing yourself to come back to one in between. If you don't allow this, then it gets a little difficult, right, to make the case work. Okay, so if there are, let's say, 100 steps, then this would become 98 steps. But you allow yourself to come back to one by in 98 steps, because the 2 steps, is you understand the first and the last step. Okay, but then you're allowing yourself to come back to one, and then that helps you to view that problem in terms of its smaller versions, right? Like you never come back to one in between, and that's like 96 steps of previous question of the smaller version, and so on, right? If you allow yourself to come back to one in the second move or fourth move, and so on. Okay, so I can't hear. Hello? Yeah. Yes. No, I can't hear. There is a lot of extra noises coming. Can you maybe mic, if you have a mic or something? No, there is extra noise coming. You can also type it in the worst case. If, yeah. Yeah, maybe there's some extra noise that's. Yes. Yeah, I can hear myself and so on. Yes. No. Try speaking. Yeah. Meanwhile, does anyone else have questions? Yes, now it's perfect. Yeah. Uh, what do you mean by problem before it? No, but also the problem is slightly changed, right? So okay, let me say it. So let me say this. So you had 2n steps, right? Then what we did is we reduced it to 2n minus 2 steps, let's say. So you had 2n steps, and here it was, you have to go from 0 to 0, okay, and not before 2n steps, not before 2n steps. Then we removed the first and the last step, right? By removing the first and the last moves, first and the last steps, we have 2n minus 2 steps or 98 steps and so on. But now it's like going from 1 to 1, okay, can hit one in can hit one earlier, yeah, but not allowed to go to the left, okay, or not allowed to hit 0, not allowed to go below the x-axis. Yeah. Yeah, this is the thing. Now this is slightly different because the flavor of the question has changed, right? Not hitting before. See, this you can this you can also write this as 0 0 0. Right, that's just a translation. That is, they'll not change the problem. Not allowed to go to -1. Yeah, that is the same thing, right? Yeah, that is the same thing. Yeah, but that is the point, is that the flavor of the question has changed. Here we did not even allow you to hit 0 again. Here we are saying, okay, you can hit 0, fine, but you're not allowed to go to -1. You're not allowed to go to the left. Okay, this is the reduction we made. Okay, now in this means that in this now you have 2n minus 2 steps. You are starting at 0. You can come back to 0 in between, but you're not allowed to go to the left. Now this we can reduce to several cases, right? What was the first case? First kind of cases, you never hit 0 earlier, right? This was the first case where you never hit 0 earlier, and this was like you hit 0 in the second step. Yeah, in it won't be third, you have to be fourth or sixth, yeah, in second step or in fourth step. So basically you have to do the casework on the first time you hit 0, right? So if that first time you hit 0 is 2n minus 2, then that's never. Zero for the first time. Actually, that's the first case. The never hitting 0 earlier means that hitting 0 at 2n minus 2 step for the first time, right? Yeah, so actually I've done it. Yeah, but then you see this problem would be like 2n minus 4 steps. Yeah, that is the thing. Yeah, so let's yes, that is a little, yeah, that's what we have to see. Let's say 100 steps, this goes to 98 steps. So you have 98 steps. Let's think about this. So first we had 100 steps. Okay, we reduced it to 98 steps, and you can hit 0. You have 98 steps, but you're not allowed to go to the left. In this, the first case is you never hit 0 earlier. Now my claim is that this reduces to 96, problem of 96 steps. Now the answer is on the screen. See, when it was 100 steps and not hitting before, You reduced it to 98 steps allowed to hit before. But now this is like never hit earlier, 98 steps. Won't this reduce to 96 steps of this problem? Yes,
Trying to see it.
yes. So see, when you had the problem of 100 steps, 0 to 0 not hit before, and it's 98 steps, 0 to 0 can hit earlier. Now this, in this subcase, we are saying 98 steps, 0 to 0 not hit before. You're not allowed to hit 0 before 98 steps.
Six steps in 100.
Okay,
Then we will reduce it to 4.
right.
And then I can, then I have 3 spaces to fill between 1, 2, 3, and 3, 4.
Right.
So, then what happens? How does it reduce? Like here you say 98 becomes 96.
Yes. Why does the 100 become 98?
Because the first and the last step is
You remove it, right? And then you reduce the problem to hit, allowing to hit. Now this is the same thing, right? 98 steps not hit before. You again remove the first and the last move of this. You see, this reduces to 90. Yeah.
reducing.
Yeah. So this reduces to 96 steps of the star problem of this. This is, it's the same reason for 100 went to 98. Not hitting in 100 steps means hitting in 98 steps. Not hitting in 98 steps with obviously means hitting in 96 steps, right? Yeah. So this is it's a little yeah, but it's yeah. Okay. So you have to use this kind of things to solve the problem for the case of 5 and 6, sorry, 6 and 8, 6 period, sorry, 10 and 12. Then you'll get more intuition. Okay. So, but the answers we saw, it's 1, 1, 1, 1, 2, 5, 14. Yeah, and there are more. Okay. Let's go to a different problem. Okay. Yes, let's go to a different problem. Okay. Suppose you have, so this is again the baby version of this we already did, but this is going to be, I'll just do it from scratch basically. So suppose you have what should I say? Let's say you have 5 variables. Say, let's say X, Y, Z, W, and U. 5 variables, you can imagine their numbers or whatever. 5 variables. Okay. Let's say you want to multiply them. Okay. Well, the question really is, yeah, and let's say that they are placed like this. Okay. So let's just say they're placed like this. That is because usually numbers, it doesn't matter how you multiply, but there are things where it matters. But in any case, here, let's imagine they are like this. Okay. Basically, in how many ways can you evaluate these 5 things? Okay. So for example, I mean, I shouldn't say multiply. I should say how many orders of evaluation. One minute. Okay. Yeah. How many orders of evaluation? For example, I can say that I'll first evaluate the X and the Y. whatever that operation is, let's say it's multiplication. Okay, I'll first evaluate the x and the y. Then to the answer of this, I will evaluate z. Now these things will matter if there are different operations, right? If mod, mass, so on. But let's keep it simple. Then I'll evaluate this. Then I can say, okay, now I will evaluate this too. Right? And then I will evaluate the result of all this, the result of this, and the result of this. So basically, when I ask a question of what are the different ways to evaluate this expression, I'm basically saying what are the ways to put brackets, right? Basically, yeah, ways to put brackets legally. Is it fine? We have 5 things, so obviously we'll just need 4. Sorry, not 4. We need 3, right? We need 3. Yeah, we need 3 pairs of brackets, right? Can anybody say a different way of bracketing it? Mm-hmm. Right. Yes, right, right. But this is another legal bracketing. Not every bracketing is legal, right? I mean, in the sense that that's obviously very obvious. Like I cannot. I don't want to do this. I don't want to. I cannot start with. Obviously, but I cannot do this. Okay? Yeah. So basically, I have. So if I have 5 variables, then basically it means I have 3 open brackets, 3 open and 3 closed brackets. So basically we can just remove these things. It just boils down to a legal bracketing. Okay, and basically if I'm interested in number of legal bracketings. Yeah, so again, this is the exactly as this previous, you can already see, right? This is not what this is just a bridge between the next question that I want to do. But this you can easily see is just like the previous problem, right? What is a legal bracketing? Well, anything in which I mean, at any stage, the number of closed brackets is never more than the number of open brackets. Yeah. Only 2 at a time. Yes, you have to evaluate only 2 at a time. So this is these are all binary bracketings for binary operations. Right. Right. So that's why you will need 3 brackets. So when you have 5 expressions, you will need 3 brackets. And then basically I'm asking number of legal bracketings, right? And that basically means, say a sequence of 3 O's, open brackets for O's, and you have 3 close brackets, and just a number of close brackets shouldn't be more than number of open brackets, right? So you can, so do you guys see that this is exactly the same problem as the previous one? The answer would be the same. Does everybody see that? Okay. Right. Okay. Just like from 1, you can come back to 1, but not go to the left. It's just the same thing. So try to write it. But that was, now the real question is, and this is in fact how, let's not say it now. Yeah. So let's say that I want to count. Let me write the word. It's called binary trees. I'll say what this means. This is extremely simple structure, so nothing fancy. Just the name is okay. Count binary trees. So if you want to count things like this, okay. Okay, give me 1 minute. Okay, now let's just draw it here. So basically you want to count structures like this, where you have to start with a point, okay, and then from every point you have either no or two children. Okay? One is left child, one is right child. So everything, if it's divisible, it divides into two things. Okay, and then it goes on. Let's say this has a left and the right child, and yeah, and then let's say this has a left and a right child. So at each step you just keep going down, and then every point has a left, has either two children, has a left and a right child, or no children, right? These have no children. This this Now those who have seen graph theory would obviously know what this means, but that's not needed. It's not needed, not being advantages at all, I think. Point is that these green things are called leaves. Okay, this is just very obvious, right? Things that don't have further children, they are called leaves. You can just imagine that's how it should be named, right? So these are the leaves. So we have, how many leaves do we have here? We have 2 to 4 leaves. Okay, so 4 leaves. Right. Let me just make a tree with not 4 but 5 leaves, so that we'll see the connection more directly. So we have 5 leaves. Okay, so this kind of structure is called a binary tree. It can be defined rigorously by recurrence and so on, but you can understand what this means from here. Binary means that at every stage you need to have exactly 2 children or no children. Okay, and the things that don't have further children are called leaves. Let's say you have 5 leaves. Okay. This is an example. Now remember, the left is different from the right. Okay, what do I mean? I mean that, for example, this these two are different. These two examples are different. These are not equal. Because here the left child, so for the second level, the left child is this tree and the right child is this tree, and they are different. Okay, so what the left child has in the second tree, so in this example, the left child has a certain structure and that is different from the left child with this. So they're different. They're not the same. Okay, so these two are different examples. Okay, but remember, we are not numbering anything. We are not numbering. I have not already not numbered it, right? Not numbered anything. So that's why it's different from counting trees, which some of us have done in the graph theory class. Okay, and it's not easier, but it's just different. Okay. So in this way, the question is, how many different trees are there with 5 leaves? Okay, right. So the question is this, right? Now let's try to solve this. So just give me 1 minute. Let me make it small. Will not need much of this. So the question is, how many different these are also called complete binary just binary trees. Let's say trees. Let's say I am asking trees with. Let's just do with 2 leaves. With 2 leaves, how many would you have? First, right? You only have one tree like this. This is the only possibility. Okay. See, this is not a possibility. This is not counted because this guy has only one child. That's not allowed. You either have two or none. So this is one. Okay. With four, let's make three. With 3 leaves, why not possible? Yeah, in this case it's possible. Yeah, so this is, yeah, it is possible. And someone said two, so I think it is two. So this is one way. So basically the first main ancestor needs to have two, and then you have to just decide either the left child has the two or the right child, right? So this obviously just be two. Okay, let's quickly move on. Let's do for 4. Yeah. Yes, yes, yes. So this is one example. Yeah. Mm-hmm. Yeah, so that's the other. Yes, yes, yes. When the left child has two further. And you can see these are the only 2 cases. Right? Okay. Because you will need to have 2 or 0. Every vertex needs to have 2 or 0. So these are the only 2 cases. Right. Okay. Now can anybody count for 4 with 4 leaves? Just one. Okay, so someone is saying, okay, so what are the two? Since there's already more than one, so what are the two? So, okay, this one is certainly there. So this is one. What is the other? The first and the second level will look always same, right? The first has 2 children, that's default. But after that, we can start changing things.
Like the sort of and
Uh, uh, yes, yes, that will, yeah, that's fine. That, yeah. Ritam, what, can you complete your question?
yeah, I was just saying that so we just remove left child left parent. Like if you could just number
Yeah, no, so I'm not numbering intentionally. You can just say based on the levels.
okay, so the second level's children can be
Second level's children could be moved to the third level.
yeah.
How? 2 leaves. Which 2 leaves?
Second level, if we remove these two children with it together.
below. Uh-huh. Oh, so you can remove both.
Yeah, like introducing a new level.
Hmm. Right. We already have 4 leaves. Right. You get 2. Right. So, okay, fine. But then, okay. So in this way, how many are we going to get?
2 more cases, so 3.
See. Okay, try. Let's see how many people you guys can get.
We could again shift this to the whole 3.
A mirror image you can take and so on, right? So when you do all that, you will see. But the reasoning is, I don't know if that will extend, but the answer will be 5 again. Let me try to give one reasoning. Now, obviously, all these reasonings combined you can do. Just one small thing is that if you start like this, yes, you're going to have um, 5 leaves in total, right? So if this is going to be a leaf, if this is the leaf, or green means leaf, right? Yeah. If this is going to be a leaf, then you need 4 more leaves. Sorry, you need 3 more leaves, right? From this tree, you need 3 leaves, right? We need 3 leaves in this tree. That is just the previous problem, right? So that's 2. Yeah, if the right child is a leaf, then you get 2 because you reduced the smaller case. Now, as people said, mirror image, but I'll just say it in terms of left child, right child, because this language, otherwise there'll be confusion because there's so many different types of trees and different notions of equality and so on. So if I call this, yeah, now if the left child is a leaf, then again, the responsibility is on this to create 3 leaves. But does everybody see now it's the same problem? Because that's again going to be a binary tree, same structure, right? You already see that will give you 2. Okay. What's the third case in which none of them are leaves? None of them are leaves. So if none of them are leaves, then it's not very difficult because then you will have to do this, right? And okay, let's. No. I'm saying in the second level, right? In on this level, right? I mean, yeah, we're doing cases on that level. Yeah, that's right. So if the left child, meaning the left child of the second level, meaning the left child of the first level, yeah. So in the second level, this one, we did those 2 cases. Now, when none of these 2 on the second level, if none of these 2 are leaves, then they will need to have children. Now what? But now there's no other way, right? This is already 4. I mean, now all of them have to be children. Third level, everybody has to be, sorry, third level, everybody has to be leaves. There's no other way. It has to be 5. You see, I mean, it's not really very faster or anything, but that's because it's a small case. But you can see it, you can kind of see a similar kind of flavor. I'll just leave it at that with the previous problems. With 5 leaves, again, try to count. 6 leaves, count. But this is 5. But I want to show a connection. 1 minute. Yeah. Okay. So what was the first question we did today? So this was 0 to 0, right? And then we had these parenthesization. And then we have these binary trees. Okay. We don't know the answer to any of them, but we have techniques to do the small cases. Okay, that is needed, and you need to spend more time on churning out semi-small cases and then see. But we have already seen that these two are, we have already seen the connection between these two. Right? 0 to 0 in 100 steps means that 98 parentheses means 49 open, 49 closed. Right? These two, everybody understands, right? These two connection we have already seen. Yeah, because these two are of the same nature as you have to go up, eventually you have to come down, but not going below some threshold. So these two are similar. But we know that these also have connections because, I mean, one of them is connected means all three, because the answer is same, right? We are seeing that the answer to this binary tree problem and to this 0, 0 problem and this, they are coming out to be the same for small cases. But now the question is, how do we connect them? Is there a good way to show a connection? That's what we want to explore. So connect, now I'll just put this because this will guide us to, because all these things are the same sets, right? They are the count, they have the same cardinality, they basically are in some sense they're same. But the decorations that are there on the set, meaning that they have been given different meanings, right? Once we are giving the meaning in terms of binary trees, once we're giving in terms of parenthesizations, and so on, right? But so the decorations is what gives us the things, and we will use one of them, we'll see will be easier to find a formula, other ones will not be so easy to find formula from, and so on. But right now we want to, because this I think is interesting and it's not that difficult also, we want to connect parenthesization and binary trees. We want to see a connection between these two things. Right. We want to show that, let's say 5 variables parenthesization, meaning 3 parentheses. 5 variable parenthesization is same as tree with 5 leaves, and so on. N variable parenthesization is tree with n leaves. And if anyone has seen logic gates, anything similar, circuits, you can see the connection easily. But let's move towards that in either way. Yeah, we have enough space here. Let me, so as a hint, so let's see, we want to see that if you have a tree with 5 leaves, then it is sort of a particular tree with 5 leaves is like a particular way to evaluate 5 variables, or same as to legally parenthesize, put a legal parenthesization with using 3 pairs of parentheses. Okay. So let's take a particular tree with 5 leaves. Let's take a particular tree with 5 leaves. We already have, no, this one we kind of distorted. Let's take this tree with 5 leaves. How does it, can you imagine how this thing somehow represents taking 5 things and evaluating them in a particular sequence? Let's turn the tree upside down. This is how computers basically calculate. I mean, the classically, even the polynomial theory that's studied using computer science. Let's turn the tree upside down. Now the leaves are not brackets. No, the leaves, will I say the leaves are brackets? No, the leaves are not brackets. The leaves are like these 5 variables. that are the inputs. Yeah. Let's just draw the tree upside down then. So yes, so you have this leaf. No, that's not how it is. I mean, I should just simply draw the tree first, right? Yeah, let's draw it carefully. There's no need to rush. Then from this we have 2, and then again we have 2. And let's draw the edges. Seeing it upside down might show something. Now these are already leaves. These are going, and the inner child there had. Okay, so you see you have one leaf, another leaf, another leaf. Same tree, I've just reflected it about x-axis, upside down. Okay. Now you can imagine that 5 variables are coming in. Now, I mean, just for the visual, I can just increase the length. Doesn't matter. I mean, it doesn't change anything, but it just maybe improves how we see it. Sorry. Let me draw this carefully. Do you guys see any connections? It's like these 5 variables have come in. Right? And the way you evaluate them will actually give you a tree. I find it hard to write it. That's a different thing. Just take a minute and just think. Yeah, it is like evaluating W and U and writing it here. Right? The W and U were evaluated together first, and Y and Z were also evaluated. So I will not say putting X, Y, and Z in a big bracket. But yeah, you can say that if you're reading from below. But I will, since it's like the variables have come in, and we decided to evaluate a few of them without changing the order. Like X and U cannot be evaluated together; they are far apart. Okay, but Y and Z can be evaluated together, or X and Y could have been evaluated together. But in this, we have made a decision to evaluate Y and Z first. And then to the result of Y and Z, evaluation of Y and Z and X, we are evaluating X with that. But Y and Z have been evaluated, the bracket will be there. And then, yeah. So you see, this gives us a parenthesization. It will obviously be legal and so on. And these are evaluated now. And then to that, we are evaluating. Well, this is how computers are supposed to evaluate. I don't know exactly what happens inside, but this is how the model is. There's a theory called circuit complexity theory. Basically, even a polynomial is represented like this, and it's studied. Then, how many steps are needed to evaluate a polynomial. Can you do it faster and so on? Or this model is the fundamental in that. But for us, is it okay that any tree gives you a certain way in which you have to, in certain way in which you can evaluate the variables? And how many variables? The number of leaves. So in the leaves, the variables come in, and then you decide, okay, which 2 are you going to evaluate? Then those 2 become the children of the previous level, right? And then when you evaluate with the next, and then these become the children of the previous level, and so on. You can explain. So now, does it make sense now that these are the exact same problem? Again, we don't know the answer to any one of them, means in general answer, but we know they are the same.
Is it like evaluate like the innermost bracket, the variable like that?
Yeah, in the sense that what becomes innermost would be decided by which two are children of just the previous level. Then they will kind of become innermost. Like W, like U and W are also in some sense innermost, right? Like they are also evaluated first together, and X and Y are also simultaneously evaluated first together, right? No, it is not like it is not like a traversing, but it is like going from one level to the other. So you're going from the level of leaves to just the level before, right? So when you are on the level of leaves, and that's where the variables have all come in. No, no, no. But no, 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 no. In fact, see, in fact, we are not interested in what the final answer is, but the final answer will all be the same, right? We are interested in how many different ways are there to evaluate. Like how many different journeys are there from 0 to 0. Eventually, you will come back to 0, or eventually the answer will be X, Y, Z, W, whatever, right? But what are the different ways in which you could have evaluated this expression? Right? And there are many ways. Suppose you get, like, sometimes we choose, right, okay, let me multiply these two numbers, but I know how to multiply them, right? And we are biased towards, let's say, multiplying 7 into 7 rather than 7 into something, understand, like with squares, like you understand, right? There's some bias will be there, so you multiply, like if this is like this. Yeah, so there will be different ways. Now, if I give you this, it's an instinct to evaluate this two first and evaluate this two first, and maybe then you can arbitrarily make a choice, evaluate this two. So I'm not saying the final answer. The final answer is always going to be the same. That's associativity. But in fact, these questions become tremendously important in non-associative places, and they come up in all kinds of things. But for us, don't want to. So that's not important. Point is the different ways in which, and this will actually, when you have power rings. I was going to say this, but then I have to say this is not a well-defined thing. Here you have to mention the order in which you evaluate. They will all give different answers. This, and you evaluate in different ways, you get a different answer. Obviously, take some smaller numbers and check. I mean, you can just check for 2 to the power 2 to the power 2, and you see the different ways to, like, if you do this, right, or maybe 3, otherwise you might get the same. I don't know. And then this is not a well-defined thing. You have to mention, I evaluate this 2 first, and then you evaluate this, you get 2 to the power 8. But if you say no, I'm going to evaluate this and then evaluate the answer of 2 to the power 2 to raise to the power 3, you get a different answer. 4 to the power 3, they are not the same. Right? So, but here it matters. But I'm not interested in that, which operations matter and where it doesn't matter. All that's algebra. I'm just interested in what are the different ways in which what's the different journeys? What was the entire, like, how would your rough sheet look like? Okay, by evaluating. So what are the different ways? Now that reduces to what are the different ways to parenthesize, but you don't need 5 parentheses, you need 3 pairs. Okay, but that order in which I evaluate, let me show the reverse. So let's forget about the tree. Let's just keep these. Let's keep this tree, but let me draw it in a different way. Maybe the fact that I went from the tree to the expression, let's go from the evaluation to the, I mean, let's just make a tree for this, right? So in this, you see 122, I decided to evaluate first, right? So it means that I evaluated this two first. This went through the gate of multiplication gate, whatever, right? And it got multiplied. 23 is still waiting, not evaluated, right? 25 and 20, sorry, 24. Maybe I can put light circles. Yeah, I'm not trying to make this very rigorous, because if I make it rigorous, then yeah, one has to be more expert with the language and so on. So let's not make it rigorous. The flavor is here only. So then you see 25 and 24 also, not then, but 25 and 24 also were evaluated together. So you see, you get this. Now to the result of 122, what did we evaluate? We evaluated 23, right? So 23 and this got evaluated, right? So they become children. Things that were evaluated to each other, they become children of of the previous level, right? So you can see, you can go to the tree now. You're getting a tree. See? Now we are evaluating this and this. So again, you can join them to the sister. You get a tree, right? So every time you do an evaluation, you kind of get a tree, and it's a level to level thing. If two things were evaluated together, then they become the children of of a parent, not ancestor, just the parent, obviously, right? This and this would be the children of a parent, right? And then this and this would be the children of a parent, right? This is tremendously important, because how many multiplications are totally needed, and can you reduce it, and so on. All these things cannot be done if we don't understand the tree structure, or this is how multiplication is understood in computer science. Okay, like what's the complexity of evaluating a determinant and so on. Okay. But now, is it clear that from a tree you can go to an evaluation, and then from an evaluation process you can go to a tree? Okay. But you have to think, you have to now spend more time and think about these things, maybe take more examples, find out the answers for these things in bigger cases and so on. Okay. Yeah, next time I will not show more connections like this, but we'll try to find, because finding the answer is also important. What is the answer to these questions? Okay, well, yeah, let's just keep it for the next class. Yeah, it's already, yeah. Okay. Yeah, so are there any questions? And also we will continue this thing during the week, I think. And in the the juniors class, in which Ishana and Pragya are there and Unab is there, um, uh, these are the people who will have to attend that, and others can their choice. Not this class, this was slightly we went. And next time we will start with a different topic there. Okay, that's for you three. I'll maybe start with yeah, some geometry or something, or inequalities. Okay, because we have, yeah, it's already, it's interesting, but we have to do things also. And this we will continue throughout the week. I'll mail and so on during the week. Yeah. Okay, are there any questions? Take your time, take a minute, 2 minutes, and see if there are any questions with respect to what we have done today. Yeah, just go over everything and see.
It, in that time, one question we asked with square, so it was a square diagram, and then we were taking fractions and like it went on exponent, square,
Hmm. Hmm.
that problem I wanted a
Okay, okay.
one is the various fraction.
Mm-hmm. Okay, okay, yeah, yeah, exact thing. Yes, yes, yes. That we didn't complete it. Yeah, we didn't complete that, and that's actually an exercise in geometry. It requires the idea of similarity, homotheity. Yeah, I think only one of I think only Shyam had done it in the test. Okay, so I will do that. Okay, anyone else has questions regarding today's thing? Okay, no. Yes, yes, yes. Yeah, that is the thing. So lattice questions are, I don't usually find them in a book. Like all these is, I just do it from different, uh, like some of them I just make and try to answer, and then I find and I study from. No, so I don't know. Yeah, but just continue solving the things, the problems that I give in the class, and obviously I've recommended you the texts, right? So the key, the yeah, I've already told you, yeah, the texts, try to do from them, right? They have the general problems in counting. Yeah. Okay. Anyone else has other questions regarding this counting today's thing? Okay, right. So then no question. Then you can leave. But I will try to do that Pragya's question. We can try to do now. Okay, I don't know if I can do it now because I myself have not thought about it since then. But let's try to do it. Okay. So yeah. So we are basically, the idea was to, let's do it in general. The idea was to add this, right? 1 r square r cube r to the power 4 and so on, right? Yeah, we wanted to add this, and obviously we know what the answer is. It's just summation, but we wanted to do this geometrically. So yeah, how is it that we had done it? Let's see. So we made a square, right? We had made a square, and then what did we do next? Right, so the square was of length 1, so just write 1. So this we can break it up, right, into r and 1 minus r. And then what did we do? We think we can make the square here. Yeah, should that be a square or should we have a square? I mean, either ways you'll get the answer, I think, to get. Right. So Pragya, was this roughly the picture to start with, or? Yes, right? So this is like this. And right. Okay. So what next? That's r square. Yeah. Now we have to see some similarity. 1 minute. No, but this no, this one should be, it does not matter, but wait, this one is 1 minus r and this one is, yeah, we can just do it in this one, right? So what I'm saying is we can make a copy of the bigger square ABCD inside this one with the structure, right? So with that in mind, we have to make a square. We have to make, with that in mind, we have to make a square here. What should be, so remember the goal is to make a copy of the square ABCD inside the square CEFG, right? We have to make a copy of the square ABCD inside CEFG, okay, with the structure that ABCD has. So in particular, this square, I'm not labeling it further, this square AF square, this will become here, right? What will be the dimension of that? If this is R, then what should this be? You see, ABCD has contracted, right? ABCD had length 1, but CEFG is kind of contracted, right? To what ratio? 1 has become 1 minus R, right? 1 has become 1 minus R, so R will become R times 1 minus R. Is that good? Yeah. Now again, this is just the motivation. I mean, one can just draw the picture, and but I don't remember, so I'm just drawing the motivation to the motivation, and it's important to think. Yeah. So this is, so we understand that that should be 1 minus r. Obviously, it becomes much simpler. Yes, yes, yes. So let me then label this. Okay. So we f I j, but why I? Anyways, f I j k. I don't know. I, okay. No, no. So the point is that, see, when you look at the bigger square ABCD, right? The bigger square ABCD has a square in the corner that is AXFZ. Okay, it has a square in the corner AXFZ. Right. Now we have contracted. So suppose this is the point which is fixed, and this big square ABCD is getting contracted. When it's getting contracted, the A is coming to F, right? The B is coming to G, right? And the Z is coming to D. No. Sorry. Yeah. So what I'm saying is completely wrong there. Yeah. The A is coming to F. The Sorry, what is happening? Just help me. Yeah, the A is coming to F and the D is coming to E. Yeah, whatever, right? You can understand that square is getting contracted. Yeah. I mean, yeah, the D is coming to E, the B is coming to G, and in fact, the Z will go to K, right? And the X will go to I. You can now, yeah, that's the more correct way to say, right? So in that way, AXFZ is getting contracted to FIJK. AXFZ is getting contracted to FIJK, right? So what should be the dimension of FIJK? It should be R times 1 minus R, because initially it was R and the contraction ratio is 1 minus R, because this is 1 minus R. The side was 1, it became 1 minus R. So if the square was R, it should become 1 minus R times that, right? 1 goes to 1 minus R. So R should go to, you can prove this by similarity and so on, but it's very clear by just pictures. Okay, so yeah, now it is just like it's a very interesting thing. It's not a fractal, but it's a infinitely. Anyways, let me see if I can finish this. So I'll just remove these because we'll need to. Okay, right. So this is 1 minus R. So this was 1 minus R, right? So this thing will become 1 minus R square. This thing will become 1 minus R square. Are we going anywhere? Is it? So this is.
How with the sum of this pictures with
That is 1.
area.
Yes, yeah. I mean, yeah, sum of the picture means that the total area is 1. And we are basically going to count that area in it. We are going to compute that area in a different way, right? So this will also be 1 minus R square, this thing, and this again will become a square, and this time it will be 1 minus, this will become a square.
Then if we are trying to show that this is bounded, then
No, but you don't need to. It's obviously bounded, right?
yes, because it is within this.
Within, but I have not yet shown that this thing is inside this, right? I have not yet shown that, and in fact, it is in some sense not. But we will have to modify and show that dividing it by something, then it becomes inside. So it's a little involved. Yeah, that time I just left it. But yeah, but the point is that initially you had a square R. So that area is r square. So this area, right? That's r square. Then I'm just shading it out. This area is r square times 1 minus r square, right? If we continue like this, then what will be the contribution of these diagonal squares? I mean this square. So that is not the total thing, obviously. Yeah, but just the diagonal squares. They will never really come. It will never really end. Okay, right. So what will be the contribution? You see, you can check. It will become like this. Every time you're going to multiply by 1 minus r, the area is going to get multiplied by 1 minus r square. That pattern is not changing. Right? This thing here will become r times 1 minus r square. This thing. Because again, it will get multiplied by 1 minus r. Yeah, is that okay? Yeah. See, the scenario is the same, right? Right. Let me let me also verify it. I said it by some reason, but this is 1 minus r. Yeah, this is 1 minus r, and this is 1, and this is 1 minus r square. So the shrinking ratio is again 1 minus r. So yeah, that's right. You are right. That's correct. Yes, yes, yes. Yeah, this is yeah. You're probably not even. Yes, yes, yes. So sure. This we did long time back. So, and I will record it also. But anyways, yeah, yeah. So tomorrow is Monday. The school. Yes, that's right. I also have class in the morning. Anyways, so this thing, and but then you can see that in this way you are going to get 1 minus r to the power 6 and so on and so on, right? You're already getting a geometric progression. Yeah, but that is not the whole thing. Now you have to, in the same way, count the other things also. But that's not difficult. What are the other things? Let's just do this. Let's do it. So this one is a rectangle, right? What is the area of that? R times 1 minus r, right? So uh, we have gotten the diagonal squares. Now we have 1 r times 1 minus r rectangle. Now again, same thing. What will be this rectangle?
No, the repeat. Yes, I am r and 1 minus r 1 minus r square.
Yeah, that's right. That's r times 1 minus r cube. That's right. That's right. Yeah, I think this is what you'll get. Right. This is right. This, but then you'll just continue this, and now you can, it will hold 5. And I mean, if you have to write it, you have to write it, but it's true. But then, have we covered everything, or have they missed anything? We have missed this green. Maybe I can say green. This green square. This green rectangle. But that is the same. That is the same as a yellow rectangle.
It will be how? It will, yes, sir. The same.
Right. That will be 2 times that. Right. That will be the same as this one. So it will be 2 times this. Am I right? Yes, right? Yeah. Now we have covered up everything. Right? Okay. So now this should add up to 1. So we have a hold on something, right? Some identity has come. Let's write it. And now basically you have to just manipulate that identity and you will get this one. But let's do it. I have not done it myself. So maybe I did it long time back. Let's do it. Yeah. So let me shift this. Yeah, because This is a beautiful way to do this problem. Okay. I think I had seen this in some magazine. It's not my idea. Okay. Obviously, later on I tried to put a reason to it and so on, but some magazine, some proof without words thing, kind of thing. Very awesome. It's just yeah. So this is thing and yeah. So what do we have? We have this this series. Let's so first I'm writing this one. If we write it in front, then we can understand maybe. Yeah, but it's not. It is still not done. One has to still do some manipulations, but it's kind of better than this. And then this is only r, right? This is not r square. It's not r square. It is only r. Okay. So and it's 2 also. 1 minus r. 1 minus r cubed to the power 5 and so on. This we know is 1. Now this is still something, right? This is like this just geometry gives us this. This is something. I think this.
Calculate this, maybe it will cancel, right?
Which
The term.
why? Which terms? Which?
So this then how? Because we are getting one.
Mm-hmm.
This becomes very small and it will.
No. This is 1. That doesn't mean that this will be. I mean, you obviously know this is not 1. This initial thing is not 1. Yeah, this is not 1. Yeah, from here we have to somehow get right. Yeah. So now you have to use. Now I know what to do. Just think. Okay. From here you have to do some manipulation. So what you have to do is you see this result is true for any r, right? So you have to put r equal to 1 minus r in this expression, and then maybe you'll because this by itself doesn't give us anything. Or 1 minute. Yeah, no, this doesn't give us, right? So you have to do some, yeah, so do some manipulation. So now there's some simple manipulation that you have to do, and you will get right. What manipulation you have to do? I think yeah, you can just do put r equal to 1 minus r, right? And you will get like this series. Yeah, try to complete this. I think yeah, this will work. Then you have 1 minus r, right? And then you put r in this one only. Same, no, in this equation, because the equation is true for all r. You can put r equal to 1 minus r, right? These are the usual manipulations, and you get this. Now this series looks more like what we want. But the problem is there is a 1 minus r square and there is 1 minus r. That's but you can just yeah, but some cancellation and so on you can do. This will become, you can take the 1 minus r down, you kind of getting something. This becomes 1 minus r. Yeah, you try to complete, you can see you can get it this, and you'll have 2 times r cube and so on, r to the power 5. This 1 minus r. Now you're almost there, right? If you just multiply with r, you see, and then just multiply this out, you will see that it will cancel and you will get this. Okay, I mean you have to, because this is the formula. No, I mean no, sorry, this is already there, right? In you don't have to multiply by r, sorry, as you were saying, some sort of cancellation, right? So in this one, in just I've just not done anything. I've just put r equal to 1 minus r. Basically, if this was in the book, they would have directly done the right thing. They would have taken this 1 minus r and taken this as r, right? I didn't know, so I did it like this. Okay, but now here, this is okay, right? This is fine. Now you see, you can just multiply this out. You get 1 r. I'm just multiplying out the left side. So basically, I should have done this instead of 1 minus r, I should have taken r. That's why I'm having to do this manipulation. Otherwise, you don't need any manipulation. Then I just take the 1 minus r down and I get this, and I open this up. I get this. But then when you take minus r, this is the good thing. You get minus r cube, minus r to the power 5, and so on. But this 2 will save us. You have 2r cube, 2r to the power 5, and so on. This is 1 minus, this is still this, but then you know what's happening. It is getting cancelled and getting it. So yeah, you don't need any manipulation, more or less, and you should not, because then the whole point of using geometry is lost, because these proofs, in the sense that you shouldn't have to do any calculation, right? And maybe I still did a little bit calculation. That's also not needed, in the sense that you can just take the 1 minus r common and get it, because you shouldn't even need to divide ideally, because eventually that's what it means, that you should not use any arithmetic, as few arithmetic as possible, and you should get the proof. Yeah, this has significance. Yeah, yes.
Sir, if I had taken my square as 1 minus r,
Uh-huh.
then my rectangle would be
Yes, exactly. Yeah, then you would have directly got this second equation, right? We need the second equation, right? We don't need the first one, actually, right? But I didn't know, so I just did it for r. But then I know that it works for all r. I mean, when I'm seeing these things, 1 minus r square, 1 minus r to the power 6, I know that these are not what I'm interested in, right? I'm interested in r square. So I just put r there, and instead of r, it became 1 minus r. And yeah, so yeah, this is, I think this is very very nice idea. Yeah, basically key the key is that we are kind of using a translation, like this thing we are kind of translating, right? We are translating it in this direction. Yeah, but we want to keep it inside this, so we are multiplying, and so it's like a multiple of it is inside it. But this is the same idea which is used in the arithmetic proof also. Now if you come to the arithmetic, what is happening, 1 minute. If you come to the arithmetic, now you see this is a very new idea, but it's not a new idea. This is what is called as a translation invariance. This, in fact, the idea we'll be using to find the answer to the combinatorial questions we were using later on, you'll see. But the point is that we are shifting this and it is not changing, right? Translation invariant, not changing under shifts. Obviously, you have to shift it in an interesting way. So the same thing is with this also. See? So the idea is that if you look at the proof of this and so many C series, yes?
we are shifting this and getting
Yes, exactly. You're kind of getting the next term. And that is how you also solve this, because how do you solve this in the generic way? You multiply it is by R, right? And this series, you know, the series becomes, this one becomes R, this becomes R square. So basically you shift it, but nothing much changes. And this is because it's an infinite series, right? Because it's an infinite thing, you can shift it and it doesn't change, more or less. Right? There's some small change you have to make in the beginning. There's no one here. That's yes, you could say that. You could say it's kind of that. Yeah, basically on some level, yeah, it's like there is an infinite abyss here. Yeah, nothing changes. So when you add something, it doesn't change. Yeah, this is like a geometric version of that. You shift it to the right and it does not change. Okay, this is why this is a fundamental principle due to which summation of infinite series is sometimes easier than summation of finite series. Okay? Summation of infinite series is easier. I mean, there's nothing like always or anything, but it's usually easier. Well, usually means something that arises naturally will be easier, because you can use this property of infinity that you said, right? You add something, it doesn't change. It's like this is a shift, right? I'm doing an operation, but that is just shifting the series. I'm not getting some extra terms. And that's making the calculation extremely simple. This is the idea that is used to solve recurrences, generating functions, and so on, which you'll see later. And there's the same kind of idea that used here, but we are not used to this language. Had we been in maybe 1000 AD, we would be more comfortable with this than this calculation. Yeah, because that time people used to do the geometrically, everything more or less. Okay. Yeah. Okay. Okay. So those who are there have they understood this? Are there any questions? Okay, no one is here. Okay, I think because it went very long. Okay, then thank you. Bye. Yeah, thank you.